Hi there. So in this section, we're going to look at composition of functions. Over here on the left, a composition of functions notation. This is important to take away here. This F, and it looks like it's kind of like a sideways 0 or an O. F, that 0 there stands for followed by g of x. I know it kind of looks like fog, but that's not what it means. It's F followed by g of x. I more often write it in this notation, and in this notation, either way, it's always read as F of g of x. Okay. For these composition of functions, you will always be working from the inside out. So you'll compute your g of x function and then take that answer and plug it into, in this case, the f of x function, because you're working from the inside out. We'll also be, again, interested in the domain. As I've said before, anything that you see in this course, you don't brain dump, you continue to use it over and over again. Okay, so domain is one of those things. The domain for composition of function is the intersection of your interior function with the resulting function. Of course, I'll demonstrate that for you here in a few moments. A lot of times, if you draw your attention over here to the right on the screen where I've written here in purple, a lot of times I always get the question is, well, where would we use a composition of functions? So I thought, well, probably a good one that you could maybe relate to would be converting money. Okay, so let's say we had 100 US dollars and we were trying to convert those 100 US dollars to euros, and we didn't have the exchange rate that would take me directly from from US dollars to euros. And so that's what I've set up here, is that I've got this first equation, f of x, takes me from US dollars to Canadian dollars. Then the second equation down here, g of x, takes me from Canadian dollars to euros. So I can use a composition of functions within these two to convert my $100 into euros. And so it would look like this. So you're trying to find you're trying to find your euros, so that's where you want to land. So that's going to be the last thing that you do. You would first have to take your 100 US dollars and convert it to Canadian dollars, then convert the Canadian dollars to euros. So that's why I have it here, g of f of x. Our x in this case is the $100 that we're trying to convert, so this would be g of f of 100. Like I said, work from the inside out. This says go to your f function. Everywhere you see an x, plug in 100. So f of 100 would be 100 divided by 0.7586. And when we do that, that should land you at 131.82. So that gives you 131.82 Canadian dollars. So now to convert these Canadian dollars into euros, you're going to go, so now we've found out that this f of 100 is equal to 131.82. Now we go to our g function. Everywhere we see an x, we plug in 131.82 because those are our Canadian dollars. So that's 0.64 times 131.82. And that will land you at $84.36. $84.36. Well, actually, this would be 84.36 euros at that point. Okay, so just that's the mechanics of composition of functions. All right, so I'll do example 1 here with you and let you try example 2 on your own. In example 1, they give us f of x and g of x, and they want us to find f of g of -3. So, like I've said before, work from the inside out. So you've got to find g of -3 first. So that says go to your g function. Everywhere you see an x, you're plugging in -3. So 2 times -3 plus 8, -6 plus 8, and that gives us 2. So that's g of -3. So now what we found, okay, well, we found that this equals 2, so now I'm trying to find f of 2. Go to my f function. Everywhere I see an x, plug in 2. So f of 2 would be 2 squared minus 2. 2 squared, of course, is 4. 4 minus 2 is 2. So f of 2 then is 2. And that 2 there is your final answer. So that we can ultimately say then f of g of -3 is equal to +2. And that would be your final answer. Okay, we plug -3 into our g function, got a value of 2, plug 2 into our f function, and got a value of 2 as well. Okay. All right, I'm going to let you pause the video and try example 2. Let's look at example 3. Example 3, the only difference here is that you are not putting in a value, you're just doing a function within a function. So here we want to find g of f of x. So if we work from the inside out, replace f of x, so f of x is x cubed minus 5. Now this says go to your g function, everywhere you see an x, plug in x cubed minus 5. So x cubed minus 5 squared minus x cubed minus 5, right? Now we take this x cubed minus 5 squared, remember that's in parentheses, so I need to write it twice. X cubed minus 5 times x cubed minus 5, because I'm going to need to FOIL that. This is, as we've said before, is a -1 that needs to be distributed to the back here. So let's do that. Minus x cubed, negative times negative, +5. This first set of parentheses, you're foiling it. So x cubed times x cubed, when you multiply, you add your exponent, so x to the 6th. First, outside, x cubed times -5, minus 5x cubed. Inside, -5 times x cubed, minus 5x cubed. And then last, -5 times -5, +25. Now let's just combine like terms. So I have x to the 6th, -5x cubed, -5x cubed, and -1 will give me -11x cubed, and then plus 30. So that is g of f of x. Final answer. Now it wants the domain. So remember from up top, it says that you need to find the domain of the interior. So the domain of the interior, it's going to remind you of that. So the domain of your interior here, that's f of x. So if we look at our f of x function, this is just a cubic function. If you put it in your calculator, you can see that it goes down and to the left forever, up and to the right forever. So its domain, -infinity to +infinity. The domain, then you follow up and look at the domain of your result. So the domain of your result is your g of f of x. That's this function here, the answer that we just found. This is another polynomial function, so you're going to see that it's going to go to the left forever and to the right forever. So that's also going to be negative to +infinity. And then ultimately the domain of g of f of x is where these two overlap. And if you think about it, they're going to overlap everywhere. So your overlap, final answer for the domain, -infinity to +infinity. That would be your final answer. Okay, let's flip it on over. Top of the next page, you have here f of x. And this is where you're just plugging f into itself. So like I said, just work from the inside out. So f of, replace f of x. You know f of x is 3x plus 2. Now this says go to your f function. Everywhere you see an x, plug in 3x plus 2. So you have 3 times 3x plus 2 plus 2. Distribute 9x plus 6 plus 2. Combine like terms, 9x plus 8. Okay, and that would be f composed with itself, f of x. Final answer. Okay. Now in example 5 and 6, we'll take a little deeper dive into finding our composition of functions and stating its domain. In example 5, we are finding h of k of x as well as k of h of x and stating the domain of each of those. So I think, yeah, I need to do both of them. Okay, so here in example 5, h of x is given and the k of x are given. So if I want to find h of k of x, replace k of x with the square root of 6 minus x. And then go to your h function. Everywhere you see an x, plug in that square root of 6 minus x. And anytime we substitute in, always use parentheses. Now hopefully you remember, anytime you take a square root and you square it, you just get what's inside. So you have 6 minus x plus 4. And then let's just combine like terms. So you have negative x plus 10, or if you were thinking 10 minus x, the same thing. So we have just found h of k of x. Final answer. Now, like we were doing on the previous page, you want the domain of the interior function. So the domain of my interior function this time is k of x. So the domain of k of x, let's think about that. K of x has a radical, an even radical at that. So that means then it's got some restrictions. That argument underneath the radical needs to be set greater than or equal to 0 and solve for x. It needs to stay positive, right? We can't take the square root of a negative. Subtract 6. Negative x is greater than or equal to negative 6. Divide by negative 1. So x is greater than or equal to positive 6. So we're getting, oh, I divided by a negative. Ooh, gotta catch myself. What happens when you divide by a negative? Change that inequality sign. Okay, there we go. Now we're back on track. So now, interval notation, x less than or equal to positive 6, then that interval notation would be from negative infinity to positive 6, parentheses, and a bracket. Then we look at the domain of our resulting function. So we look at the domain of h of k of x, this guy up here, and hopefully you recognize that's just a straight line, right, with a slope and a y-intercept, and so those don't have any domain restrictions. That would be negative infinity to positive infinity. And then to find out what my overall domain is I'm looking for where do these two overlap. If you need a visual, just I'll just draw a quick little number line here. Get myself don't give myself enough room over here. If I put in my positive 6 and I have a bracket and I'm shading to the left, and then the other one is going from negative infinity to positive infinity, then I'm looking for where the blue and the green lines are on top of one another, and so then that would have to be then my overlapping, my final domain would have to be from negative infinity to 6. Bracket. That would be your final domain there. Okay. All right, let's come over and look at the next example. I want to, just switching it around here, k of h of x. Working from the inside out, replace h of x is x squared plus 4. Now this says go to your k function. Everywhere you see an x, you're plugging in x squared plus 4. So now, notice how I used a parenthesis there. That's super important because there's a minus sign in front of that would need to be distributed. So this would leave us with the square root of 6. Actually, let me go to the side here just to save myself some space. This would be the square root of 6 minus x squared minus 4, which would ultimately give us the square root of 2 minus x squared, or negative x squared plus 2. Either way you want to say that. This would be your k of h of x. Okay, that would be k of h of x. Now, finding the domain, look at your interior function. So the domain of h of x, back over here. Here's your h of x function. This is a parabola. It doesn't have any restrictions, right? So domain of h of x, negative infinity to positive infinity. The domain of the result, we've got to think about here that since I've got a square root, it's an even radical, what's underneath that square root needs to stay positive. So negative x squared plus 2 has to be greater than or equal to 0. Now, this one's a little different. It's not linear. Everything that we've done so far has been linear, meaning it's just x to the first power, but since this is x to the second power, we're going to have to treat this a little differently. And so what's going to happen is that we're going to need to set negative x squared plus 2 equal to 0 and find the zeros. And from there, this is fairly straightforward. We'll just subtract 2 from both sides. So negative x squared equals negative 2. Divide by negative 1. So x squared equals positive 2. Then to get x all by itself, take the square root. So then we find out, well, x equals plus or minus the square root of 2. Now, from here, let's draw the graph of this negative x squared plus 2. You should find that it looks something like this. And these values, where it's crossing the x-axis, those are your zeros. So we're going to say here then that this value and this value, this is going to be your negative square root of 2, and this is going to be your positive square root of 2. Remember from the beginning, we're interested in where this is greater than or equal to 0. So think about what makes sense. If you're going to be greater than or equal to 0, does it make sense for that to be above the x-axis or below the x-axis? And hopefully you agree that it makes sense for that to be above the x-axis. So we can see that we are greater than or equal to 0 when we are between this negative square root of 2 and positive square root of 2. So we can say then that our domain here would be from negative square root of 2 to positive square root of 2. That would be our domain for the result. So now our overall domain is where this negative infinity to positive infinity overlaps with this restriction. So hopefully you would agree then that the domain then of k of h of x would end up being that negative square root of 2 to positive square root of 2, because that's where it overlaps with negative infinity to positive infinity. If you think about it on a number line, if you've got negative square root of 2 and positive square root of 2, and that's one restriction, we've got brackets there, and then the other restriction just takes us all the way, the whole number line, where the blue and the red on top of each other between those two values. Okay. All right, let's look on down here at example 6. Again, you might want to pause the video and try as much as you can on your own first. In example 6, they're giving us a function for c and p, and they want us to find c of p of x and state its domain. Work from the inside out. Replace p of x with 2 over 7 minus x. And then go to your c function. Everywhere you see an x, plug in this 2 over 7 minus x. So I have 1 over the 2 over 7 minus x minus 5. Now this looks ugly. We've got to clean this up. We cannot leave, you got a fraction within a fraction. The easiest way to get rid of this fraction within a fraction is to multiply by the common denominator. And the common denominator is you look at the fraction within a fraction, so you just have to worry about here then the 7 minus x. So we're going to multiply every term by 7 minus x. So up top, 1 times 7 minus x is just 7 minus x. On the bottom, 2 times, or on the bottom, when you do 7 minus x times this term, the 7 minus x's cancel out and just leaves you with 2. And then you have minus 5 times 7 minus x. So now from here, I have 7 minus x up top. Let's clean up the bottom. I've got 2, and you take this negative 5 and distribute it. So I have negative 35 plus 5x. Let's go one more time and still clean up. So 7 minus x over on the bottom, 5x minus 33. That would be, this is now your c of p of x. C of p of x. That's that composition. Now it wants the domain. Go to the interior. You need the domain of p of x. We need the domain of p of x. So my p of x function has a denominator. So that denominator cannot equal 0, right? So set that equal to 0 and solve for x to get your what's excluded. So subtract 7 from both sides. Negative x cannot equal negative 7. Divide by negative 1. So x cannot equal a positive 7. So my domain that I'm getting from here, negative infinity to 7, parentheses on both, unite that with 7 to infinity. Now look at the domain of your result. So the domain of my result, I need to make sure that my denominator here, 5x minus 33, does not equal 0. Solve for x, so add 33. 5x does not equal 33. Divide by 5. So now we're saying x cannot equal 33/5. So if we think about domain in this regard, then it's going to be negative infinity to 33/5, and then pick back up at 33/5 and go to positive infinity. Now, in order to find my overall domain, I need to figure out where these two overlap. Draw you a picture. Think about overall domain here. So I'm going to put my 7 down here first. Here's my 0. Here's my 7. 7's got a parenthesis, and it's shading both ways. Shade to the left forever, shade to the right forever. It can equal any number but 7. It can equal 6.99999 and 7.0001, but it cannot equal 7 because 7 makes the denominator equal to 0. 33/5, I just put that in my calculator. It's 6.6. So then I come over here and I'm going to make this 6.6. And then I've got parentheses on either side of it. And I'm shading to the left. And I'm shading to the right. And I'm looking for where they overlap. So anywhere the green and the blue lines are on top of one another. So remember, this is 33/5 here. So it goes from negative infinity to 33/5. Pick up and go from 33/5 to 7. Then pick up again and go from 7 to infinity. Okay, and that's your final answer there for your domain. All right, that would be your section 2.3. Flip it over and I've got your section 2.4 notes. In this section, you're looking at symmetry and odd and even functions. There are 3 types of symmetry. You can be symmetric to the x-axis, the y-axis, and the origin. And when you're symmetric to the x-axis, then I'll just sort of draw you a quick picture here. This would be a good example of something that is symmetric to the x-axis. And so being symmetric here to the x-axis is just a mirror reflection over the x-axis. Remember, this is your x-axis. Here's your y. Okay, the algebraic test to determine if a function is symmetric to the x-axis, you replace y with negative y. So it's kind of opposite of what you would think. If you're testing for symmetry to the x-axis, you replace y with negative y. And if you get the same equation, then it's symmetric to that axis, the x-axis. Likewise for the y-axis, if you have a function that is symmetric to the y-axis, so good easy one to give you here would be a parabola. And so now with this parabola, I can definitely tell that I'm symmetric to the y-axis. If I were to flip it over the y-axis, it'd be directly on top of one another. The algebraic test for being symmetric to the y-axis, for your function, you replace x with negative x. And if you get the same equation, then it's symmetric to the y-axis. And then lastly, for the origin, example I can give you here. Try to something like this. Try to do as best I can freehand here. But to be symmetric to the origin, you flip it over the x-axis and then the y-axis, and then these two pieces are ideally supposed to be on top of one another. It's not perfect here, of course, me just drawing freehand, but hopefully you get the idea. The algebraic test for testing for the origin is that you replace both x and y with their negative counterparts. And if you get the same equation, you're symmetric to the origin. of course, you can always look at the graph and see it that way as well. I'm going to do example 1 with you. And I'm testing for symmetry. I'm going to test all 3 so you can see, because it is possible for a function to be symmetric to more than one. Just because you find that it's symmetric to, the graphs that I just showed you here are only symmetric to one axis, but there are examples that you can be symmetric to more than one. So let's run through example 1 here together. In example 1, I'm going to first test for the x-axis. And so like I said up top, the test there is that you replace y with negative y. So it's one of those things, it's one of those rare things where it's kind of counterintuitive. But I replace y with negative y. And I've got to get it back to a positive y. So in order to do that, I would just divide by negative 1. And so then that tells me, okay, well, y equals, anytime you take a function divided by a negative, then you're just going to have the negative of that function. Well, that's not the same as the original function. You're always comparing it back here to this original function. So we are not symmetric to the x-axis. Right, now let's move to the y-axis. So remember up top, the test for the y-axis is you replace x with negative x. So go to my function, y equals 1 over negative x. Well, nothing really I can do there. I mean, usually we typically write the negative up top, but still this is not the same as the given function. So again, I'm not symmetric to the y-axis either. And lastly, let's look at the origin. Remember the origin said that you take x and make it negative x, and y with negative y. Do both. And if we get the same function, then we are symmetric to the origin. So in our case here, we're going to have negative y equals 1 over negative x. We want to clean this up, so we're going to divide by negative 1. Cancels out and becomes a positive y. Over here, a negative divided by a negative gives me a positive. So this is indeed the same as the original given function. So yes, in this particular case, we are symmetric to the origin. Okay. In example 2, I'll let you try that one. I've shown all my work on the solution key, so I think you'll be in good shape. All right, let's flip it over on the next page and talk about odd and even functions. Those of you going on to take trig and calculus, you will see odd and even functions again. Okay. There's a slight correlation between symmetry and being odd and even. If your function is symmetric to the y-axis, then it's automatically an even function. The test is if f of negative x equals f of x. So if you plug in negative x to your function and you get the exact same original function, meaning all signs stayed the same, the function's even. If your function was symmetric to the origin, you can automatically say it's odd. I think that one's pretty easy to remember, origin odd. The test here is you still plug in f of negative x, but if you get negative f of x, meaning all of your signs change, then your function is odd. I know that probably doesn't mean a whole lot to you at the moment, so let's come down here and do some, okay? And we'll give you, I did put a note down here, you'll always be finding f of negative x. If all signs stay the same, then your function is even. Maybe I should use a highlighter. If all signs stay the same, then your function is even. If all signs change, then your function is odd. If there's a mixture of some staying the same and some changing, then your function is neither even or odd, okay? The first two I had us just draw upon whether our functions were looking at the graph, looking at their automatic symmetry. So hopefully you would agree here in number 1, you are symmetric to which axis? Hopefully you'd agree that I'm symmetric to the y-axis. So since I need to get back to a pen. So since I'm symmetric to y, then I am automatically an even function. Okay. Moving over to number 2, I'm not symmetric to the y-axis. And I'm symmetric, in this case, symmetric to the x-axis, and being symmetric to the x-axis does not have any variance on whether you're odd or even. So in our case here, we would be neither. I'll say here neither because we are symmetric to x-axis. Remember, if you're symmetric to the y-axis, you're even. If you're symmetric to the origin, you're odd. But if you're symmetric to the x-axis, it would be neither. Okay. All right, so now let's in examples 3, 4, and 5, and 6, what we'll be doing our test. And what the test looks like is that you always find f of negative x and then determine, did all your signs change? Did they all stay the same? Or is there a mixture? So f of negative x in this first one, everywhere we see an x, plug in negative x. Definitely use parentheses on these. Anytime you take a negative and raise it to an even power, that always, always, always comes out positive. So that would be positive x to the fourth. Minus 2. Take this negative and raise it to another even power. That's going to be a positive x squared. So now compare the original to what we just found, f of negative x, what we just cleaned that up to be. All signs stayed the same. So this function is even. Okay. Come over to number 4. Find f of negative x. You're always finding f of negative x. So everywhere we see an x, we're plugging in negative x. Take a negative and raise it to an odd power. They always come out negative. So then this is going to be negative x to the fifth. So it's going to be negative times a positive 3. So I'm going to have negative 3x to the fifth. Now my next term, if I take a negative and raise it to an odd power, it's going to come out negative. Times the negative 6 will give me a positive 6x cubed. And then lastly, negative times negative, positive x. Now go back and look from original to what we just found, f of negative x to be. First term, signs change. Second term, signs change. Last term, signs change. So all are different. So since all are different, we can say that this function is odd. All right, move on down to number 5. Find f of negative x. Everywhere you see an x, plug in negative x. Clean that up. That leaves you with negative 3x minus 9. Now we've just found f of negative x. Compare it back to the original. The first sign changed, but the second one, negative 9, still stayed negative 9. There was no way for that to change. No way for that to change. So this is what I refer to then as a mixture. So therefore, this would be neither odd nor even. In example 6, this one can be tricky. So I want to go ahead and do this one with you, because this one, if you just rely solely on the signs changing, it might trip you up. So I'm going to be sure that I point this one out to you. It typically only happens when you have rational expressions. So if you have a numerator and denominator, this is the only time you're going to have to kind of worry about or think about this extra step that I'm going to show you here. Still, everybody see an x, plug in negative x. So up top I've got a negative x. On the bottom, negative x squared plus 4. Let's clean that up. So up top, still negative x. Take that negative down here and square it. So that comes out to be positive. And if you look at this problem and say, well, the top changed but the bottom didn't, so this must be neither. Well, be careful. Back up here at the top, we said that in order to be odd, f of negative x had to equal negative f of x, or negative 1 times f of x. Wouldn't it be legal for me to rewrite this function here as negative 1 times x over x squared plus 4? Doesn't that really equal the same thing? X squared plus 4. So, right, because if you multiply that negative 1 through, you'd only multiply it up top, and you'd be right where that previous step. So here, what we've just shown then is that f of negative x equals negative, and this x over x squared plus 4 is f of x. So this is indeed odd. Okay. Again, you're really only going to have to worry about thinking about that if you have a rational expression or rational function here with a numerator and a denominator. Okay? All right, hope this helps. Let me know if you need anything. Thanks a lot. Bye. Oops.